Yes? All right. Over the last 100 years, the universe hasn't changed much. But our perception, our understanding of the universe has changed immensely. When we look out to the universe now, we see galaxies, we see distant quasars and gamma ray bursts. These are objects that would have been foreign, at least in our current understanding, to astronomers 100 years ago. The idea of black holes, these massive compact objects that, when they get too close to other stars, have the gravity to siphon off the material through accretion disks and pull that material around into hot plasma. The idea that our galaxy is filled with other planets would have been an uncertainty 100 years ago. And certainly the size, scale, and scope of our universe would have been foreign to astronomers 100 years ago. And that got me wondering, if I approached an astronomer at the turn of the century and asked if it were explained the nature and view of our universe as we understand it today, would they have believed it? Or would they instead thought that universe was impossible? Welcome. For those of you that don't know me, my name is John Millis. I'm a professor of physics here at Anderson University, and I'm honored to kick off a new lecture series hosted by our School of Science and Engineering here at Anderson University. I encourage you to come to these talks, as they promise to be very lively and engaging throughout for the course of this semester and next. We'll be hearing talks on the excitement of chemistry, which promises to be an explosive time. We'll hear from one of our student biology faculty about the Ebola virus and some of the possible ways that might be cured. We'll hear about the beauty of mathematics. We'll hear about how computers might be taking over our world. So I encourage you to come to this lecture series, as it's going to be a whole lot of fun. My talk tonight, I've entitled The Impossible Universe. And my journey for this talk, the inspiration, has come as I've begun to think about what the universe looks like to us today and how our viewpoint has changed in the last 100 years. This is motivated a little bit by the fact that we just celebrated the 100th anniversary of an important equation or thought, and that is Einstein's theory of general relativity. This one equation, or set of equations, really changed the way that we view our universe, or at least allowed for possibilities that we didn't know existed. And I sometimes wonder if Einstein himself even recognized the implications of his theory, of the things that he was writing down, what that would possibly lead to in the future. When he was writing down his theory, this was his view of the universe. You may recognize this as the Milky Way galaxy. If you go out into a dark stretch of sky and you peer up into the night, you would see this band coming across the night sky. Okay? If the galaxy that we inhabit, the bright part in the middle, is the center of our galaxy where a supermassive black hole lies. But that wouldn't have been known, necessarily, 100 years ago. And in fact, this galaxy that they would have been seeing, they thought was actually our entire universe. This is a rough idea of what our Milky Way galaxy looks like if we were able to escape outside and look back at our home galaxy. It's a barred spiral galaxy. We call it a barred spiral because it has this bright bar across the middle and these spiral arms that wrap around. To astronomers 100 years ago, this would have encapsulated all of our universe. This would have been all that there was. It would have been static, unchanging in size, and that was the viewpoint that they had at the time. Now, of course, you may be sitting there wondering that, well, I know a little bit about astronomy, and 100 years ago they were aware of other galaxies, and that's true. They were aware of them in principle, but they didn't call them galaxies. They called them nebulae. This is a picture of the Andromeda Nebula, as it would have been known 100 years ago. And while they're aware of these objects, they put them in the classification of other things like supernova remnants and planetary nebula, other objects that had these fuzzy structures in the night sky. About 100 years ago, about the time that Einstein was working towards his theory of general relativity, the excellently named astrophysicist John Millis, no relation, was actually working on this object and others similar to it to try to explain how these spiral nebulae would naturally form in the universe. They were using interesting physics and ideas of collisions and things to kind of create these spiral patterns. Of course, it turned out that that work was all for naught because these objects weren't nebulae within our own galaxy like they had believed. It was the work of this man, Edwin Hubble, who began to look at these objects and seek out specific types of stars, specific types of objects within these nebulae that he could study. One in particular was called a Cepheid variable star. These are stars that have very specific properties, and that over time they can actually swell and contract and swell and contract. And as they do that, they change in their brightness. Now, it turns out that you can demonstrate that the amount or the period over which it changes its brightness is proportional to its absolute brightness. Therefore, we can calculate how bright the objects should be simply by looking at the period. This provides a very powerful tool, because by doing that, we can discover that these objects are not nearby. He was able to locate a Cepheid variable star in the Andromeda Nebula, and from his measurements of the period of oscillation, was able to calculate its intrinsic brightness. And from that, he was able to then do another calculation to calculate how far away the object was. And it wasn't located in our Milky Way galaxy. It was instead located in a galaxy millions of light years away. Further studies revealed that lots of objects, even farther away than that, populated our universe. Our universe was not so small anymore. In fact, it was populated by immense numbers of galaxies. Every object, every dot of light that you see in this image represents a whole other galaxy, filled with billions upon billions of stars. This particular image is a rather famous one, called the Hubble Ultra Deep Field image. It was actually gathered by turning the Hubble Space Telescope to what looked like an empty point in space, where there didn't appear to be very many stars or anything of significance in that region. They pointed this telescope and took a long exposure to gather as much light as they could. And this is what they found, that even in what appears from Earth to be a dark region in the sky is in fact filled with galaxies, thousands upon tens of thousands of galaxies. And these objects populate our universe. So this begins to raise an interesting question. How big is the universe? What is it made of? Again, 100 years ago, they were thinking simply about the Milky Way galaxy as the end-all, be-all of everything that we experience. But as it turns out, the universe is filled with much more. But this is only part of the story. We actually discover that there's a bit of a problem. Most of what we see in the universe, most of what we see, stars, galaxies, hot gas, only makes up a tiny percentage of what's there. It seems that the universe is dominated by these two things that we call dark matter and dark energy. And in fact, everything that we see in the universe and can measure directly is about 4% of the universe. So what is this other stuff, this so-called dark matter and dark energy? Well, it's a good question. But I want to start by saying that this is not a unique problem, or the first time that such a problem has arisen. In fact, the whole dark matter problem has been a theme within astronomy and physics for more than 100 years. Astronomers in the 1800s were taking measurements of the planet Uranus, and they were calculating its orbital parameters as it went around the sun. And as they took these detailed measurements, they began to notice something, that the positional data that was predicted by Newton's laws of physics didn't match with what they were seeing. The physics of the time said that the planet should be moving in one way, but something seemed to be perturbing that orbit. They were faced with a dark matter problem. Either something was out there affecting the orbit of the planet, or their theory was wrong. Now, of course, what the astronomers did is that they first looked to see if they could find an object that would explain the perturbations that they were seeing in the observations. They did some calculations and figured out that, well, if another object is out there, then it must be here. They looked, and they discovered this. Now, of course, or what's interesting about the planet Neptune is that it had been observed previously. Astronomers were aware of its existence, but they didn't realize that it was a planet. It's so far away from the sun that its transit across the night sky is very slow. And so the observations that had been made previously, the astronomers hadn't recognized that it was in fact a planet. But then when they began to study it, they realized that it was actually part of our solar system, and that its presence was actually causing the perturbations in Uranus's orbit. So the solution to that dark matter problem, if you will, was that there was some missing mass, some missing object in our solar system that was throwing off their data. Around the same time, scientists were beginning to make detailed measurements of the planet Mercury. This is Mercury passing in front of the sun. And as they were making these detailed measurements, they began to notice that, the orbit of Mercury seems to be different than what would be predicted by Newton's laws of physics. So again, they're faced with the dark matter problem. Either there's some missing mass, some invisible matter, some as yet undetected thing that is causing the orbit of Mercury to behave erratically, or perhaps our theory of gravity is wrong. In this case, it turned out to be the latter. Newton's laws of gravity, while they do a very good job of explaining the way a ball flies through the air, why the planet Mars orbits the sun the way that it does, when in an intense gravitational field, it doesn't work as well. Okay? You need to actually use a theory that's more precise, that can handle the little perturbations caused by such an extreme environment. And of course, what happened was Einstein wrote down a theory of general relativity, and his equations were able to account for the perturbations in the data seen from Mercury. So that brings us to the 1930s. In the 1930s, an astronomer named Franz Ricci was observing the motion of galaxies. And he was looking at the motion of galaxies within clusters. And he began to notice something peculiar. Their motion, their relative proper motion, didn't seem to make sense. They didn't seem to have enough mass to adequately account for how they were moving relative to each other. It was as if there was some other mass or some mysterious force that was drawing the objects together. So, of course, we're faced with another dark matter problem. Either our theory of gravity is wrong, Einstein's theory of general relativity, the leading theory of gravity at the time, or there is some missing matter in this system. Franz Ricci proposed that the solution was dunkle Materie, German for dark matter. He was, of course, ignored because it was such an extreme thing to suggest that these galaxies, these clusters of galaxies, were actually filled with far more mass than we could see. But then, of course, other measurements were made. We looked at things like spiral galaxies. We began to take detailed measurements about how they rotate. We began to calculate how they should rotate given the mass that we can see. And of course, what did we find? We found that they didn't rotate the way that we calculated that they should, the way that Einstein's theory of general relativity predicted. And again, we went and said, okay, well, if it was in fact a problem with the mass, how much mass would we need to fill in the space in order to make it rotate the way that we see it rotate? And of course, it was a lot. About 4 times as much mass as we could see. It's quite a bit. So, what's going on? Well, we're faced with a classic dark matter problem, and we're forced to begin thinking about what is the best path to resolving this issue. Is it a problem with our theory? Or is there really mass sitting out there? Far more mass than we can see that actually pervades the entire universe, that affects the motion of galaxies and galaxy clusters, the could be filling the space all around us? It's an interesting question to consider. So we begin looking for evidence of which one might be the case. One of the ways that we do this is by using a process called gravitational lensing. You'll notice that this image of galaxies looks a little strange. You'll see that you see some of them appear to be smeared out. Okay? The reason for this is that there's intense gravitational fields. There's something very massive near those galaxies that's warping the light around it. Okay? So it turns out that what you can do is that you can feed these images into a computer, do some fancy mathematical gymnastics, and calculate where dark matter would have to be in what amounts in order to cause this skewing within the image. And we find that the sort of dark matter that we see is on the order of what we would expect given our previous results. So it seems to be that at least there might be something there. But of course, we need a lot more evidence than that. This is, we call this the bullet cluster. It is in fact, I believe, 2 clusters, technically. And what you're seeing, although it's hard to tell from this image, is that you've got 2 galaxy clusters that are in the process of merging. That's why they call it the bullet cluster. The smaller cluster is moving into the space of the larger one, like a bullet embedding itself into a block of wood. Now, scientists were aware of the bullet cluster and had studied its motion, but they began to consider and make predictions. Well, if there really is dark matter present, what would we expect to see? Well, there's a few things you should know first. As much as you see in the visible in this image, all of the stars and the structures of the galaxy, which you see all these little dots on the screen, the space in between those galaxies is actually filled with gas. There's more gas in this image that you can't see than there are taken up by the stars. Okay? As much as 10 times as much gas is present. So when these galaxy clusters would begin to merge, the gas from one cluster would begin to interact with the gas from the other cluster. That process would be very energetic, and in fact it would heat up the gas and cause it to produce X-rays. So we would expect that as we see these 2 galaxy clusters to merge, that in that point of collision you would see bright X-rays. However, if there's also dark matter present, you would expect the dark matter to pass through along with the clusters pretty much unaffected. So what researchers did is they took this image and they did 2 different things. They studied it in the X-ray to look to see if the hot gas or the gas was interacting, heating up and producing X-rays. They also analyzed it for gravitational lensing and trying to calculate where the dark matter would actually be to explain what we were seeing. What they found was this. The pink here in the middle is the X-ray image, where the hot gas of the 2 colliding clusters is lighting up and producing this glow. The blue represents where the dark matter would be, okay, to produce the gravitational lensing effects. This was some of the first convincing data that was put out there for the existence of an actual physical dark matter. Because where the galaxy collides is separate than where the dark matter is located. Now I should say at this point that scientists have attempted to reproduce this type of result in other galaxy clusters with mixed results. So we still haven't really definitively nailed down what's going on here. Like I said, this was a pretty strong piece of evidence, but it's been hard to reproduce with other merging galaxy clusters. So, let's assume for a moment that dark matter is some sort of thing. It's a particle, it's an object, it's something in the universe. It's not a problem with our theory. Well, scientists began thinking about what could possibly be the explanation for this dark matter, what this dark matter could really be made of. Astronomers have kind of classified things into 2 general categories, the 2 leading ideas for what dark matter is made of. The first is the Machos. The second, which we'll get to in a moment, is the Wimps. So it's Machos versus the Wimps. Machos actually stands for massive compact halo objects. Essentially, Machos are dead stars. They're exhausted white dwarfs. They are black holes. They are brown dwarfs. They are small objects. They are massive objects that are just the result of an aging universe. They would be spread out throughout the region. Okay? They have a couple things going for them that make them attractive. They'd be formed by natural process. The natural formation and death of stars, the evolution of galaxies. These objects would naturally rise throughout the universe. They have that going for them. They'd also be massive, and they would move rather slowly. Those are also attractive features, since dark matter tends to clump together. But there's a problem. Machos would have to exist in such great numbers that we have a difficulty reconciling the ages of galaxy and star formation rates with the amount of stuff that would have to be present in these objects, in these galaxies. So while we haven't completely ruled Machos out, they certainly don't seem to be the leading candidate anymore. Instead, we tend to look at the Wimps. Wimps are weakly interacting massive particles. Now that sounds like we actually have a candidate for what these things are. And a lot of theoretical cosmologists would stand up here and tell you that there are candidates for what these particles are, but the truth is that there's a lot of possibilities, and we don't really have a lick of evidence on which it is. So, Wimps are actually a very generic term that kind of define what a dark matter particle would have to be in order to explain the data that we've gathered. They'd have to be weakly interacting. Weakly interacting simply actually kind of has two meanings. Number one, since they don't interact electromagnetically, they just wouldn't interact strongly with anything else in nature. They would interact gravitationally, but gravity is actually the weakest of all the forces. But they would probably interact with what we call the weak nuclear force. The weak nuclear force is responsible for radioactive decay. This is important because if they interacted with this particular force, that could explain maybe how they arose naturally in nature. If they were part of some nuclear decay process, then we could perhaps figure out a way to explain how all of this dark matter would naturally arise in nature. They'd have to be obviously weakly interacting and massive because we would need a whole lot of it. So something that's really light, like a neutrino, a very, very light particle, a particle that's nearly massless, probably isn't going to work so well. Number one, because you would need an awful lot of them in order to have enough mass in order to explain the dark matter that we see in the universe. But more so than that, we see that dark matter tends to be slow-moving and clumped together. Neutrinos are so light and fast-moving, they would tend to disperse quite naturally. So something that's really, really a light particle isn't a good solution. We need something that's massive. But there are a number of particle candidates that we are aware of that could possibly fit this mold, but there's also probably a number of particles that we've not detected that could possibly fit this mold. So one of the things that we want to do is that we say, okay, now we think that these particles, these dark matter things, might actually exist in nature. The only way to know for sure is to go and measure them. So that's what we try and do. We build these detectors, and I should say there's two main ways that we seek to measure these dark matter particles, directly and indirectly. The direct method presumes that dark matter particles are streaming through the Earth at all the time. And as they pass through, because they interact so weakly, they don't interact electromagnetically, that they pass through us, they pass through the Earth, and just go straight through. But occasionally, every once in a while, these dark matter particles will actually bump into a nucleus. And if they bump into a nucleus, they can agitate that nucleus a little bit and cause it to radiate a little beam of light. And if we could capture that light, then we could maybe have some evidence that a dark matter particle went through our detector. So what they do is they build these big underground laboratories. These laboratories, they fill with a dense liquid, and they wait for dark matter particles to penetrate through. They bury them deep underground, typically in mines, and things like that, to shield them from all other forms of radiation that might want to come through. So the only things that should be passing through are very light, weakly interacting particles. Now, there's actually a number of things that could still pass through and interact, things like neutrinos, like I said. But what they do is they actually use specific gases that will give off just the right light to indicate a dark matter signal. They surround the chamber with what we call these photomultiplier tubes, and as the light gets given off these flashes of light from the dark matter particles interacting with the nuclei, we can trace dark matter passing through the detectors. Sounds great. Problem is, hasn't worked so well yet. In theory, these detectors should provide us some evidence for dark matter, and we actually believe that we have detected some events. The difficulty is that the detection of these events you expect to be very rare. As we've already discussed, dark matter should pass through most things unabated, all the time, all around us. So you'd have to wait for it to bump into something. At the same time, filtering out all other possibilities of what could be passing through the detector. It's a challenging study. Over 2 years of data, this particular detector, the Xenon project, detected 12 events. 12. Over 2 years. That's not a lot. Pretty tight. So your statistics aren't very good, so it's difficult to make a claim that you've actually seen anything, but there's a hint. Okay? It's not statistically significant yet. We can't claim that we have seen dark matter particles, but we may be on the right track. We're refining the experiment, making improvements, finding ways to improve the number of interactions and improve the statistics. But we're not quite there yet. There's other experiments around the world doing similar things that have all received similar results. But luckily, there's another thing that we can do in trying to study dark matter. We can do what are called indirect dark matter searches. This is an experiment that's particularly close to my heart, the Veritas experiment, which stands for Very Energetic Radiation Imaging Telescope Array System. You can't get funding in astronomy unless you have a fancy acronym. This is an array of 4 gamma ray telescopes in southern Arizona. Each one of these dishes is about 12 meters across. What they do is they actually search for very high energy gamma rays from distant violent events that hit our atmosphere. When they hit our atmosphere, they decay into these particle showers, which create these bursts of radiation which we can then detect on the ground. It's a very tricky experimental process, but one that has been quite successful. So one of the things that we do with this is we point our telescopes to a type of object called a dwarf galaxy. Now these galaxies are like other galaxies like the Milky Way and Andromeda, except they are much smaller, okay, much smaller scale. Because of that, they don't have a lot of the intense radiation signatures that larger galaxies do. Which means that if you detect gamma rays from those objects, the only known explanation for that would be from dark matter. Because it turns out, if you have a bunch of dark matter sitting in a galaxy, the dark matter is going to bump into itself. And when it does that, it can actually annihilate and turn into gamma radiation. So if we point our gamma ray telescopes at dwarf galaxies, we might be able to see signatures of this dark matter presence within these dwarf galaxies. So far, the Veritas experiment hasn't been able to detect this, but I should say that's also not entirely surprising. The signal we would expect to see from these galaxies is very, very weak. So these telescopes don't have the sensitivity to see signals quite that weak, but we're doing some very fancy analysis right now to see if we can perhaps penetrate down and see even the slightest hint of these gamma ray signatures. The replacement experiment to Veritas, which will hopefully be coming online in the next decade or so, would have the sensitivity to really probe these dwarf galaxies and nail the dark matter signature if it's there. Luckily, there are some other indirect experiments as well. One of them is called the AMS, right here. The AMS is the Alpha Magnetic Spectrometer. It's actually an experiment that was attached to the International Space Station. The International Space Station catches a lot of flack for being horrendously expensive without producing actually much science or anything. And that's true, but in this case, this is actually a really clever experiment, relatively inexpensive, and just part of the routine development of the space station, they were able to attach this detector. Essentially what this detector does is it discriminates electrons and positrons. You don't know what a positron is. A positron is the antimatter particle to the electron. They tend to be created in pairs in very energetic events, when gamma rays bump into something and they produce these charged particles. So, if gamma rays, or if dark matter were annihilating in dwarf galaxies or in other sources, like in the center of the Milky Way, which is another place we think dark matter is annihilating, then these electrons and positrons should be streaming out. And what this detector does is it detects and counts the electrons and positrons that pass through it. It then takes that data and it compares the amount of electrons to positrons that it sees. I'll come back to that in a minute. I'm going to show you sort of a plot. It's the only numbers and data I'm going to show you tonight, don't worry. But the idea is that there should be a little bump. You should see a few more positrons than electrons if you're getting these dark matter annihilations. But I want to quickly talk about another experiment. This is another experiment that I've worked on called the Fermi Space Telescope. I wasn't involved in the development of it at all, but I've used data from it to do some of my scientific work. The nice thing about these NASA satellites is that the data is readily available to the public. So even if you're not a trained scientist, you have access to the data and the free analysis software to look at it. So you can, even if you have no scientific training at all, but just an interest in astronomy, you can go to one of these instruments, download everything you need, and start getting involved in science. And I encourage you to consider doing that. And if you want to get started down that path, I or one of my students who has been involved in these projects would be happy to talk to you about it. So this is called the Fermi Gamma Ray Telescope, and it's kind of a complement to the Veritas experiment that I worked on that I talked about earlier. This covers a slightly different part of the gamma ray energy band, the lower energy part of that. And this also looks for these dark matter annihilations, these gamma ray signals from dwarf galaxies and other systems like the Galactic Center, looking for dark matter annihilations. Now, between the alpha magnetic spectrometer and the Fermi Gamma Ray Telescope, they've been looking for the same type of signature. This little bump, this little extra piece of signal that shouldn't be there, that based on our current understanding could only be explained by dark matter annihilation. I'm only going to show you one of the plots here, but this is one of the preliminary data sets that they've shown. In the blue, you see what you would expect if there's no dark matter annihilations. The red is the little extra bump you would expect to see if gamma ray annihilations were happening in the target region. This is a preliminary data set. This is not a data set that was meant to claim definitively that they detected something, but they saw an initial hint. You see this data point here. When they fit the red line to the data, you see that little bump. If you look at the data from the alpha magnetic spectrometer, you also see a very similar type of bump in the data due to dark matter. Now again, we're looking for very, very weak signals, kind of a needle in a needle stack, if you will. And you're trying to extract just that little extra bit of signal. It's a difficult process and requires the accumulation of lots of data. So this is an ongoing process. So, I'm going to pause for a minute in the discussion of dark matter, and I want to switch gears a little bit to dark energy, because that's the other piece of the puzzle. We haven't solved the dark matter problem yet, but we've been making significant progress, and with the design of new experiments, we think that we might be closing in on a resolution of dark matter within our lifetimes. Dark energy, though, is a bit of a different animal. It's actually the result of a fairly recent study from the early 1990s, where a group of scientists was looking at the motion of galaxies. Now, Hubble, decades earlier, had found that galaxies seem to be receding away from us, that the universe as a whole is expanding. That wasn't really news. But what these astronomers were doing is they were trying to take very detailed measurements of how fast galaxies that are kind of right in between us and the edge of the visible universe, how fast those objects were traveling, how quickly they are moving away from us. And they found something particular. they found that the expansion of the universe wasn't what they had expected. That in fact, the expansion of the universe seemed to be speeding up. Now, this was a bit of a surprise. 100 years ago, when Einstein was writing down his theory of general relativity, his equations predicted that a universe should be either expanding or contracting. Remember, I told you earlier that their view of the universe at the time was that of a static universe, that our entire universe was contained within our own galaxy, which didn't appear to be expanding or contracting. So at the time, he added an extra term to his equations, what he called the cosmological constant. And essentially, the role of this cosmological constant was simply to offset the expansion that his equations predicted. Now, of course, Hubble ended up discovering that the universe was in fact expanding, that the universe was a whole lot bigger than previously thought. So scientists ended up removing the cosmological constant from general relativity. And Einstein is often quoted, at least, as having said that his adding this cosmological constant was the biggest blunder of his career. Now fast forward to today. We're faced with general relativity, which predicts an expanding universe. But the universe isn't just expanding, that expansion is accelerating. So scientists say, aha, I know, I'll add an extra term to general relativity called a cosmological constant, and that'll explain the acceleration. So, decades after Einstein removed the cosmological constant from his equations, it has made its way back. Now, we don't really call it a cosmological constant anymore. Some do. You see it appear in literature that way. More commonly, though, we simply call that dark energy. That something is causing the universe, the expansion of the universe, to accelerate. All right. So what do we really know about dark energy? Now that we've covered that, I say that tongue-in-cheek, but it's also kind of the truth. There are a lot of theories out there that claim to be able to explain what dark energy is, how it arises. Some argue that it's actually a problem with general relativity, that it's incomplete, that there's a missing term, that if we just add the right scalar field to the equation, that it could explain the expansion. The problem is that none of the theories out there have made any testable predictions in order for us to separate them. One is just as good as the next. Nothing seems to really give us any clue what the proper direction is. So we don't really know what dark energy is. All that we seem to know is that it's causing some sort of expansion in the universe, the expansion to accelerate. I really like this plot because it gives us a little bit of an idea of what the universe has looked like throughout its history. We think that initially the universe began to expand. We commonly call this the Big Bang. Now, I should say at this point too, that oftentimes when the Big Bang is discussed, even in public forums by scientists, we often tend to cling to certain views on the Big Bang. The fact of the matter is that even our viewpoints on the Big Bang are changing. We don't really fully understand what the initial conditions of the universe were. Neil deGrasse Tyson was recently quoted as saying that the universe was once really hot and dense and was really compact and sort of a primordial atom, which makes you think it was very small in size and then began to expand out. Catherine Freeds, chair of theoretical physics at the University of Michigan, commented to me recently that no, that was wrong, that in fact the universe was infinite, and that at the earliest moments, right before the Big Bang, that it was in fact much hotter and much denser, but was still infinite in size. That simply what's happened is that infinite universe has just expanded out. Okay. The point being is that cosmologists can't seem to really agree what even the universe looked like in its initial conditions. And we still can't seem to agree on how big the universe is today. Is it 93 billion light years across? Is it infinite in size? We don't really know. And in fact, that's one of the things I'm going to talk about at the end, looking forward into the future. This plot, though, sort of takes the former viewpoint, that the universe was once hot and dense and very, very small, and began to rapidly expand out in a period called inflation. This period of inflation lasted shorter than the blink of an eye, literally 10 to the minus 32 of a second. After the universe created into existence, this period of inflation happened. As the universe began to expand and cool, eventually stuff stopped moving around so fast that it was able to join together. But eventually, these things, atoms would begin to pool together into big clumps and form stars. And you got stars that began to form, these stars would begin to clump together, galaxies would begin to form, and so on. So you see this expansion of the universe seems to be kind of rolling along very nicely after the period of inflation ended. But sometime in the recent past, the expansion began to accelerate. So what we're trying to understand now is what is causing this acceleration. Is it in fact a thing, a mechanism, something in the universe itself, some form of matter, something that's actually driving this expansion? I just love this image. It doesn't actually mean anything, but it was just a really pretty picture I pulled from the interweb. And it sort of, I think the intent was to make everything sort of flowing into it, but when I saw it, it sort of gave me this vision of dark energy and the fact that perhaps everything is swirling out, that something inside is driving everything out from within and pushing the universe apart. So perhaps there's something within the universe that's actually driving this expansion. But maybe not. Maybe it's that we still need to tweak our theories. Perhaps Einstein's theory of general relativity, that we talked about when we kicked this whole story off, is incomplete. Perhaps there's something missing. Some extra term, something yet to discover. I want to end this talk by taking a look forward in what we're going to discover in the next 100 years. Black holes have dominated the news recently. This is just an artist's rendering of a system that we call a microquasar. And essentially, there's a black hole here whose intense gravitational field has gotten hold of a nearby star and it's literally ripping the material off of that star into an accretion disk. And through this process and through an intense magnetic field, it's creating these powerful jets that spit this energy and particles out across the cosmos. Recently, scientists have been reconceiving their ideas on black holes and what black holes are. Black holes were previously thought to be these sort of cosmic vacuum cleaners that just suck everything in if you get too close. That anything that goes into the black hole is lost. Any information about what it once was or is now is gone forever. But new work by several different physicists has suggested that perhaps black holes aren't as black as we previously thought. Perhaps they're more gray than black. That perhaps information that falls into these black holes can actually be preserved. Perhaps we can actually even learn and peer into and understand what's going on inside of these exotic objects. That's one thing I think we're going to begin to learn more about in the next 100 years. One that I'm very excited about, and if I ever get invited back to give another one of these public lectures, this will likely be the subject that I talk about next, is the search for worlds beyond our own, and specifically the possibility of life beyond Earth. Will we be able to find another Earth-like planet in our galaxy? In the last couple of decades, we went from being aware of only a few planets outside of our solar system to now we are aware of hundreds with a couple thousand more possibilities. And that's only in our galactic neighborhood, our little piece of the universe in our nearby cosmos. There's a lot out there. There's a lot for us to discover and a lot for us to see. And I think planetary astronomy, what we call exoplanets, are going to be really big in the next century. Someone standing up here 100 years from now is going to be likely talking about all the Earth-like planets that we could possibly visit one day. That we could possibly send signals to or probes to see if there's possibilities of life on any of these worlds. That's what's coming in the future. So, the universe hasn't changed much in the last 100 years, but our understanding has changed quite a bit. And the thing about science is that we're never done learning. Our understanding will continue to change over in the years to come. And I really look forward to seeing what it looks like decades from now looking back on just some of the ideas that we struggle to grasp now that we're finally beginning to close in on. Will we finally understand what dark matter is? Will we have a clue as to what dark energy is and how that fits in to our universe? Will we be able to find evidence of life on other worlds? It's certainly fun to look forward to. So, that's all that I have for tonight. I do want to mention a couple things really quickly before I take questions. The observatory, it looks like we're going to be able to have open tonight. I see my teaching assistant scrambling out of here so they can go get ready. For those of you that have never been to our observatory, it's on the roof of Decker Hall. I'm sure several of the faculty around here that are familiar with it will be happy to lead groups over there once we are done in this space. So I encourage you to come take a look. The cloud cover is supposed to have dissipated. Some of the seeing won't be quite as good, but we should still be able to see some really interesting clusters and nebulae. So I encourage you to do that. I want to at least give you all an opportunity to ask some questions. You all were kind enough to come out and hear me speak and sit there patiently as I ramble on about dark matter and dark energy. So if you have any questions, I'll take those now. Yeah. You mean why is that? Yeah. Did you mean like why would we expect to see that? His question was in reference to the dark matter. Why would we expect dark matter to annihilate and produce electrons and positrons? Is that what you're saying?
More positrons than electrons.
Oh, so it's not that they're actually producing more positrons than electrons. It's just that when we look out, we expect to detect electrons and positrons, and we expect to see a certain ratio naturally coming in from the cosmos. It's just that the dark matter annihilations would produce an extra bit of positrons that we wouldn't have otherwise expected to see. But the dark matter annihilations would actually produce equal amounts of both.
So how do you get extra positrons?
How do you get extra?
How do you get a bulk of positrons without a bulk of electrons too?
So, I don't remember the exact mechanism. It has something to do with the I don't remember. I honestly don't remember. I'm more familiar with the gamma ray side of the experiment. So what happens is that the electrons and the positrons are both created, but then they'll give off the gamma rays as their accelerator. So the gamma ray signal and the electron positron signal are somehow correlated. But I forget why you would expect the extra contribution from the... Oh, I remember what it is. It's because the electrons and positrons are being created at a certain energy. So what you see is you see an extra bump of positrons at a specific energy. Yeah, and so that's what it is. It's the actual energy of the positrons that you're seeing the bump in. That's what it is. Very good. Yes?
Can you go back to that picture of the Big Bang, that inflation that you told us about?
Yeah.
Is that actually growth in size?
Yes. This is growth in size of the universe. Now, again, what you're really seeing here is that the expansion of the universe, literally getting bigger. Now, if the viewpoint of an infinite universe really is true, then you have infinity expanding into an infinity, right? But it's perhaps easier to visualize if you think of it as sort of a smaller object expanding out. But yes, when you expand it very rapidly, and it would happen over such a short period of time, and the universe would grow so rapidly, that the speed of expansion would have greatly exceeded the speed of light. And in fact, in some sense, the expansion of the universe is still exceeding the speed of light. It's just that the expansion accelerated so rapidly during that period of inflation. Now, what's interesting about this is that inflation is really handy for explaining certain cosmological observations. I didn't want to get into too much of the data, but there's certain things that we see in the universe, things like what's called the cosmic microwave background, and things like that, that kind of tell us a little bit about what the early universe looked like. And inflation, we use as sort of a tool to explain that data set that we see. But what's interesting is that the inflationary theory wasn't created as sort of a cosmological solution. It was created because the physicists were trying to solve a different problem. And that was why we have an electric and a magnetic field. Electric fields are produced by charged particles. Magnetic fields are produced by moving charged particles. And trying to explain where those two forces separated out to become distinct is difficult to explain. But in an inflationary universe, it actually explains why those two forces would have been separated out. So that's actually the motivation behind why they created an inflationary universe. It wasn't until one of the scientists who had done that work was giving a talk at a university where someone noticed that, oh, that also explains these other things in cosmological theory. So it's caught a lot of traction because it seems to answer questions in lots of different areas of physics, and not just sort of the cosmological argument, but also in fundamental classical physics like electricity and magnetism. So.
I noticed in the picture it says quantum fluctuations.
Yeah.
Is that kind of an accepted view, or is that still speculative?
So his question is about the very beginning, what initially caused the expansion. In this chart, it's written as quantum fluctuation. Okay, now what does that mean? Well, the field of quantum physics says that things are constantly shifting and rearranging, and we actually expect energy to sort of move around. And so you would expect these fluctuations at the quantum level. We actually see this happening out in nature. Particles are being created and then reabsorbed into the vacuum on a constant basis. We can design experiments to measure this process. But in this case, this would have included sort of a quantum fluctuation on sort of a different scale. It sort of initiated the whole movement of the universe. I'd say at this point, from what I understand, this is sort of the most commonly quoted theory in terms of what initiated the initial expansion from the Big Bang. But I don't know a lot of the detail as to why that's favored over some other argument. Yes, sir?
A couple months ago, I was reading a basic interpretation of a Canadian physicist's study on black hole physics, and sort of her conclusion was she wasn't sure that the math allowed for black holes to actually exist in the universe.
Yeah.
So I was wondering if you could comment on that.
Yeah, so his question revolves around some work done, I think in this case by a Canadian physicist, as you mentioned, but there'd actually been other physicists in the past that had proposed similar ideas. And what they argue is that the mathematics behind the existence of black holes may not be sound. Her work, in my opinion, is flawed. And I think that's the general consensus in the scientific community and the cosmology community, is that she made some basic assumptions in her theory which are not widely accepted. In fact, most physicists have demonstrated them to not be correct. So I don't put a lot of weight behind that. But if you even look at the observational data, I think there's a mountain of observational data that suggests these objects exist in the universe in some form. That doesn't mean that we completely understand them. As I mentioned earlier, there's been sort of a shift in the astronomical community as to the real true nature of black holes. Are they really black? Do they really consume all that's around them, or is information able to actually transmit across their boundary? That's something that's still not clear. But the objects are certainly there, and they're certainly interacting, and they're certainly powerful. It's just we maybe have not accurately quantified their properties yet. They might have some properties that we hadn't considered previously, or perhaps we had oversimplified. Yeah. Yes?
I was wondering if the recently discovered Higgs Boson plays into anything related to dark energy, dark matter research.
Higgs Boson, very good. That's actually one of the things I had considered talking about today, but I was afraid of just throwing too much out there at once. For those of you that aren't aware, the scientific community has been really focused in the last couple of years with the possibility that an object called the Higgs Boson had been detected. Some recent follow-up analysis has actually cast some doubt on that discovery, whether or not it was actually a definitive discovery or not. And that's sort of a problem in science in general, is that it's not so much that you detect a signal, but you also have to demonstrate that there's nothing else that could have made that signal. That what you found really was the thing you claimed it is. And that's always really difficult. And then, of course, there's always so many different variables that you have to consider, so many things that can affect your data that you always have to do a lot of follow-up work. So it's not quite certain whether they found it or not, but that's sort of an aside. The idea is, and the whole motivation behind searching for this thing we call the Higgs boson, is trying to understand what causes mass in the universe. Particles have mass, protons, electrons, these things all have mass. And as they interact, they form larger structures that eventually form things like people, this stage, this building, the planet, the sun. All of these objects are made of mass. But what gave the original particles their mass in the first place? So Peter Higgs had proposed that perhaps the thing was a field that pervaded the entire universe, that everything around us, there existed a field that was part of the very structure of the universe itself that he called the Higgs field. Now, as particles or as anything moved through this field, it would have certain properties that as it interacted with that field, it would either cause a drag on the particle or the particle would move straight through it. If it moved just through the field effortlessly, then that particle would have no mass. If the field caused the particle to drag, the amount that the particle dragged we would perceive as the mass of the particle. The problem is that you're looking for an invisible field. So how do you actually test to see if the field is there? Well, luckily, what you can do is you can force the field to manifest itself, to sort of reveal itself to you. We do this, this actually happens all around us all the time because we see photons, we see light, okay? We can force light to be created to sort of pop out of the photon field, if you will. So that's not an unusual thing to have happen. We see particles popping in and out of existence. But we had to create just the right conditions in order for a particle manifestation of this field to pop into existence. So they did these experiments where they collided things together at very high energy to create just the right environment that a Higgs or Higgs-like particle could pop into existence. Now, the particle itself isn't stable. It immediately decays. But it decays in a very specific way. So what they were actually looking for was actually the byproducts, an indication that a Higgs particle had existed in that environment. And then, of course, you can't just find one. You have to redo it, time and time again and show and build up enough data where you can show with some confidence that you're actually creating these Higgs particles. So that's kind of, I don't know if I completely answered your question, but it doesn't really fit into dark energy in a specific way, other than to say that it's the thing in the universe that kind of gives everything its mass. So, how are we doing on time? It's 8 o'clock. So if you have any other questions, I'll stick around for a few minutes. For those of you who don't know Dr. Wallace, Dr. Chad Wallace is there at the back, and I'm sure he'd be willing to lead a group up to the observatory here soon. Otherwise, myself or Dr. Carr would be willing to take people up to the observatory if you need help finding it. Otherwise, I'll hang around for a few minutes, answer some questions. If you want to head up to the observatory, we'll probably start looking at some things around 8:15 or so. So, again, thank you for your attention. Thank you for coming, and I encourage you to continue coming to this lecture series and supporting the School of Science and Engineering at Anderson University.